Okay, so my suggestion was to take problem 4 first. If we have time, we can also look at problem 3. So problem 4, there we are looking at an elliptic equation, and that is the Laplace equation for steady equals to the heat equation. And we have a couple of boundary conditions to which we come back later. But first the question A. Does equation 10 constitute a marching problem or an equilibrium problem? Do you need an initial condition to compute the solution of this problem? So that is not a very difficult question. We don't see any time derivative in this, so this cannot be a marching problem. It must be and is an equilibrium problem. It is determined by the boundary conditions. And we, of course, do not need any initial condition for that, because it's not time dependent. So then we just state that. We say that the problem that we consider here, that is highlighted in this symbolic form, plus k t y y equal to 0, is an equilibrium problem. And as it is not time dependent, no initial condition is needed. However, if we want to solve this by an iterative method, then we need an initial guess. But this is something different. That is then just a way to solve the linear problem that we get from the discretization. But that is not an initial condition, just a guess to solve the linear system of equations. B. Discretize the interior point of the domain using the second order accurate finite differences. Express the solution in this form and state the properties, the appropriate values for coefficients A, P, and so on. So that is something then that you should of course be familiar with to have this equation and to do the discretization with the standard finite difference method. In the beginning of the exercise, it says that k is constant. So we can keep the k, and actually that was done by Jürgen in the solution that you will get, but we could equally well divide by k and get rid of it because it is constant. Of course, if it would not be constant, or if we would have a source term, then it would have to keep it, or at least when we have a source term, divide by it to get it into the source term. But if we have it like that, let's take it, let's keep it for the moment when we do the standard finite difference method for this Laplace equation. So remember, what we do is we have our grid points ij, and we have the left neighbor I minus 1, the right neighbor I plus 1, the northern and the southern. So these are then involved when we do the discretization. But in that case, we can write the k outside, and then we will have a discretization of the second derivative. That is then for t, and then we take it at I plus 1j minus 2tij plus ti minus 1j divided by delta x squared. So that will be the discretization of the second space derivative in x. And similarly, for the second derivative with respect to y, then we go in this direction, so we take the j plus 1 there, ti j plus 1 minus 2 ti j plus ti minus 1 j divided by delta y squared, and that is then equal to 0. So that is the standard discretization, and when we write it in the form 11, then...
shouldn't the last one be j minus 1 instead of...
Thank you, that's correct. That was a typo. J minus 1, correct. So when we want to have it in this form, then we want to have the center coefficient positive. So then we bring the values regarding the Tij to the right hand side. And then we can write this equation, and for simplicity, I divide everything by k to get that. So then if we do that, we take that and that to the right hand side and write it then on the left one, we get 2 divided by delta x squared plus 2 divided by delta y squared. Tij is equal to, and the rest we can keep on the left hand side. So then I do it now in the way starting so this here is then south, the north, the east, and the west, the corresponding indices. So I start with the south in that case. And the south is then related to this guy here. So that will be then the 1 over delta y squared Tij minus 1. The next will be my ordering the west, and the east, and the north. So we do this ordering as we would do when we have this standard ordering, first I and then j. That will be 1 over delta x squared Ti minus 1j plus 1 over delta x squared Ti plus 1j, and the north would be 1 over delta y squared Tij plus 1. So that would be then the equation that we get to get it in this form. And then we can identify the coefficients very easily. This is then the AP coefficient. The P is then the sitting in the center. This is then the A south, the A west, the A east, and the A north. So then we have identified the coefficients, and what is common for this is the fact that the center coefficient, the AP coefficient, is, I can write it here again, is the 2 over delta x squared plus 2 over delta y squared. And you see that is the sum actually of all the other coefficients. So that is the sum of the neighboring coefficients A and B. So that is then A, we have it here, A south plus A west plus A east plus A north. So then we see here from this we get 2 over delta y squared, and from here we get 2 over delta x squared. So then we have identified these coefficients, and in the equation 11 we have also SU, a uniform source term, and in our case that is 0, we don't have any. So we can note that the SU in our case is simply 0. So then we have established the answer to question B. Now identify the type of boundary conditions given at the 4 boundaries. Let's see. Can we get that? So let us do a little picture of what we are doing here. So here, this is the x, this is the y direction. Let's start then with the bottom boundary. At the bottom boundary we have t of x0. So here we have the origin, obviously. T of x0 is equal to some function tb of x. So what kind of boundary condition is this? The value is given at the bottom boundary. What's the name of this boundary condition? Any suggestion? Yes.
That's the Dirichlet.
Exactly. That's the Dirichlet boundary condition. The value is specified. So it is the Dirichlet. Top boundary. And the gradient is given. We have the heat flux given there. That would be such an example. That means we have given there the top, the t dy is a function g of x. So what is that? What kind of boundary condition is that?
Neumann.
Neumann, exactly. That's the Neumann boundary condition. Gradient, the normal gradient is given. That is a Neumann boundary condition. So then the left boundary, there we have a constant temperature given. So then the of 0y is t left. The value is given, now you know it, so it's a Dirichlet boundary condition. The divide boundary, let's see, we have dt dx equal to 0. So that is the normal derivative is then the x derivative, so that is a normal boundary condition. So then we have identified the boundary conditions. We usually do not treat Robin. Robin would be a combination of these two. Let's look at-
But since the derivative is 0, shouldn't it be a constant?
No.
Okay.
Why should it be constant? If you have an adiabatic boundary, so you've seen, imagine you have a heat problem, you insulate the right boundary, then the temperature derivative is 0. So that is, you don't need, and it doesn't need to have a certain value. It can be 0. We had the example with Lisa's room. There was also, I think, the floor was insulated. So then we have a similar boundary condition there. There could be dy 0. So that's fully possible. That's no problem. Okay. C is established. D. Scroll it down a little bit here. discretize equation 10 at the top boundary and the grid point next to the bottom boundary. Express the answer in a similar form as equation 11 and state the appropriate coefficients. So that means we have at the top and at the grid point next to the bottom boundary. So I move it up again. We can now do a sketch of the problem. So imagine we have our grid here. So now we are at a grid point next. We start with the bottom, that is easier. We start with grid point next to the bottom boundary. So that would be then a grid point that has the j index. It depends on how we do the indexing. In the class we did the indexing that we called this 1. And the boundary was then 0. So that is a matter of taste. So at grid point next to the bottom boundary, then we would have our AP would then be, say, if we introduce this notation, if we say the j index is 1, this index would be 0. If we say, then we want to determine here the ti1. This would be then the boundary condition here, would then be the ti0. So then we would have our equation, our discrete equation that we derived earlier, would then have the following form, would be the A south would then be the ti0 plus the A west ti minus 1, 1 plus AB ti plus 1, 1 plus A north ti2. So at this point the boundary condition will enter at this point here. Because here the boundary condition then is given by this condition here. So that means at x point xi, this will be then the condition. The boundary value ti0 will be given by the value tb of xi. So that means this here will be by the boundary condition. So that will be tb of xi. That is the Dirichlet boundary condition that enters there. And then we don't need to compute that, we have it already. So then this value will not enter our linear system as an unknown, because it is already known. So then this expression as times tb of xi will then be a part of the source term. So then we get the coefficients. AP, you see it here, we did not do any special treatment here. The AP, the AW, the AB, and the AN as before. But now, the AS is actually also the same as before. We didn't do anything special here. But the AS times TB of xi will now be a part of the source term. But the SU now will be the AS times the TB of xi. So that will then, if you think of the linear system, be on the right hand side. So for that for all the points that are next to the boundary, then the right-hand side of the there's a matrix times unknowns equal right-hand side. The right-hand side will not be 0, but it will have this contribution. Okay, so that is then near the bottom boundary. And now the more interesting point is then the top boundary. So if we are here, then we have to determine there the T, I, in my notation to be Nj. And we have to do it because we have no condition on the value, we have only a condition on the y derivative. So therefore we really have to do the discretization at the top boundary. It is at when we have Neumann boundary, we have to do it at that boundary. So we have then the top boundary. We have the Neumann boundary condition. And that was we have it over there. dt. Now we are specific. We say it is at xi, and the upper location was ly in the task. dy is equal to a given g of xi. So that is the condition that we have there. So what we do is, we do this discretization now by taking, well, I write it here. So we have here the top boundary. Here we have the value that we are considering. Here we have our grid. So that means we have here the I nj, and this will be the I nj minus 1. So that is inside our grid. So here we have these neighbors left and right. But what we also have, what we need a point here. We need a point I nj plus 1 when we want to do this discretization here by a central difference. So we approximate this then by Ti nj plus 1 minus Ti nj minus 1 divided by 2 delta y is equal to g of xi. So then we have this here, this is then a ghost point value. So we have introduced a ghost point which does not belong to our domain, but which would naturally enter if we do the standard sample discretization. And from that we see we can express the ghost point value Ti nj plus 1 by the value that we have. That is now here for this point, it is the southern point. It is the point I nj minus 1 plus, we multiply 2 delta y g of xi. So then we can express the ghost point value by known values. One from the southern point and one that is simply given. So then we use this when we do the discretization. We use our standard approximation and we insert then this when this enters. So we inserting, we have here, it starts with this expression here. Inserting for the expression was, let's see, that's the expression 11. Expression for, isn't that for the Ti nj plus 1 in the equation 11 at j equal to nj, we get. So now we write again our equation, our discrete equation, approximating the Laplace equation, which is t, that is then I, we are here then at the top boundary, then we have here the nj, that is equal to the as. Now that is no problem, that is then the t I nj minus 1 plus the a west t I minus 1 nj plus the a east t I plus 1 nj plus the a north. And here comes the thing. Here we would have the ti nj plus 1, right? But we insert this. We have shown that this is equivalent. So instead of writing this, we write this. Ti nj minus 1 plus 2 delta y g of xi. So that is what we have done. We have replaced here the t I nj plus 1, our ghost point value, by the condition that we got from the Neumann boundary condition. And then we see what we get. We get here another contribution to the southern coefficient. So that means we can then put them together. And then we get here as plus an times this value at the southern point. And the value that we get here, an times this, that will be then a source term. So let's write that. So from that we get that the AP Ti and J is equal to, and now comes the, where we take already part of the ghost point value into account. So it's entering them here, what I just said. Ti nj minus 1. The A west, Ti minus 1j, and the A east, Ti plus 1j, they are, here I just have to say this is nj. So otherwise they are unchanged. And here we have not, should not forget the part that is constant, that is in the an 2 delta y g of x I. So that is then plus an 2 delta y g of x I. So then we see here that the AP coefficient, the A double and even AE coefficients, they are unchanged. So AP, AW, AE unchanged, as we had from the very beginning in the derivation. So the AS, say I write it in this form, the mu AS is then the sum of the old and the AN. If you remember what they were 1 over delta y squared and 1 over delta y squared. So this is then 2 over delta y squared in our notation. And this part here is then part of the uniform source. An 2 delta y g of xi. And if we would do that the whole computation, this would be 1 over delta y squared. So then you can write it delta y g of xi. You see we can get rid here of 1 delta y, and we get then 2 delta y g of xi. So then we have established the coefficients. Any question on that? So that is how we can solve the standard finite difference method for, in that case, the Laplace equation with the Neumann-boundary condition. So we discretize, approximate the Neumann-boundary condition, get a condition for the ghost point value, insert that in the equation. And then we get a modification of the coefficients. Okay. So now we have to do a little shortcut here. So then we have solved, let's see, yeah, now we have solved D, E. The following code snippet is part of a MATLAB script. We have this here. So you see this is an iteration going on, and it is for the 1D steady heat equation. So it's simpler than what we started off with. Here you see that we have a similar expression. AW and AE are involved. AP, so it's a similar expression as we had before, but not without A north and A south, simply. So that is computed in first T of 1, then T of J with a loop over J, and then in the end T of Nj. And it is said that periodic boundary conditions are used. So we can see that here we would expect that it would be 0, but the 0 value and the Nj value are the same. Here we would expect an Nj plus 1, but 1 and Nj plus 1 are the same. So that is already can be seen from this small part of the of this MATLAB script. And then it says the parenthesis is used to indicate some part we won't focus on here is left out. Use the code snippet to explain the difference between Jacobi and Gauss-Seidel. What method is used in the code snippet? So what method is used? What is your answer to that? Any suggestion? You see, the values are directly computed from the discrete equation. It can only be Gauss-Seidel. It's no other way. For Jacobi, we would have first to compute a new iteration value, would have to give it a new name, because, for example, imagine we have computed the T of 1, then we are here at 2, then we will use the T of 1 here already that we have here. So it's directly used, and that is what we do with Gauss-Seidel. For Jacobi, we would have to have different names for that to be able to use it from the old iteration level. So then the difference is in Jacobi, we only stay at the old iteration level, and then we first compute all values at the new iteration, and then we update the whole solution and go on. For Gauss-Seidel, we do it as it is explained here, we directly update. As soon as we have a new value available, we immediately use it. So that is this one. And the next one is you are asked to implement, instead of the maximum iteration, to implement a convergence criterion. And there you could do it in a similar way as we did in our examples in the exercises, that you check the change from one iteration to the next, compute, for example, the 2 norm or whatever, and then you relate the one that you compute at the current iteration to the one that you have computed in the beginning. So you would then we could, for example, then use a condition of the following kind. Let's see. So you would have to implement the stopping criteria. And the one that we used was that iteration k plus 1. For that you would need really to introduce a new variable to be able to distinguish the iterations. So in this code snippet where the Gauss-Seidel is used, you don't do that, you don't need it. But here you would need it. That has to be small equal than some tolerance times the 2 norm of the value that you compute after the first iteration minus the initial guess. And that would be then we have 10 to the minus 10 or something, so if you want really to get it well converged. And here we have an iteration error. Remember, we discussed that, mentioned that yesterday in the summary. So if you don't if you have here not, you have anyway, you have some iteration error, but if you have this tolerance too high, then your solution of the linear system by this iterative method will not be good enough. So the difference between the iteration value that you have, for example, dk, and the t, where this is then the solution of the linear system, that is the iteration error. So in the implementation then, well, we have not time to do that here, but you'll see that then in the solution. We have not time now to go to 3, but I want in the end to give you a little information on the follow-up course that you have now all the prerequisites to take, and that is the course TP 4165, Computational Heat and Fluid Flow. So the general information is here, and the contents of the course is that it treats the finite volume method. So here you learned about the finite difference method, there it is the finite volume method. The other difference is the focus there a lot on systems. So we start also with a scalar equation similar as here, but with the finite volume method. And then we look at the Euler and Navier-Stokes equations, at the 2D Burgers equation, and at the incompressible Navier-Stokes equations, including the energy equation. So we have an example, I have unfortunately no time to show you, where we compute a backward-facing step. That is, we have a channel, and we have the channel widens at some point, and we get there then separation, and that is then part of this is exercise 11 in that case. There are also 12 exercises there. So it's a channel here, so we enter here. For example, in the exercise it is a constant profile entering, and then we get here a separation, so the flow goes that way. It attaches here, and here we have a reattachment, the separation bubble. So we do the computation of that in a domain that is then something like this. And then we can compute that, and we can also compute the heat transfer for that. So this is for lambda problem. And we also do turbulence. There are turbulence models, but the computation with that we do it with the CFD tool in either star CCM plus or Fluent. That will be exercise 12. So you are very welcome to this course. And let's see. We have anything? Yeah, we have something else that is the links where you can see really nice applications of what we have been discussing here. And the case that we are considering then in the laminar case, in the turbulent case it looks like that for the backward facing step, but for the laminar case, it is much easier, and we have steady flow. So that is then, and what is happening in reality is fully turbulent flow. Let's see, that is very tiny here. Okay, don't get it. I get it a little bigger, but not that much. But you see the dynamics that is going on here. Flow is coming in, and we have here totally unsteady and actually three-dimensional flow. That is computed, as I say here, by DNS, direct numerical simulation. Here we don't need any turbulence model. All the scales, all the tiny eddies are resolved. And that is a research that is actually conducted by my colleague Helge Andersson, and Jürgen, who is the scientific assistant on the course, is also working on this field. So, you have then the prerequisites to also do that, but you need a lot of computing power. It's very heavy computing, so you need months maybe to do one simulation of a big problem. For a high Reynolds number, it is impossible at the moment, but as the computers get bigger and bigger, it becomes more and more possible to do higher Reynolds numbers. So in the end, you have seen now the introduction to CFD. You have seen how you can do it. You have a lot of experience, a lot of training in MATLAB, which will be very good for really doing solving concrete fluid flow problems. And you have seen what is important to check whether you get the right results, check the solution with respect to reference solutions, to exact solutions, that is verification. And when we do things like that, we have to check with reality, to check the modeling out, to do validation. So by that, I think we have good prerequisites to do CFD. And if you want to get more, please come to TP 4165 in the fall term. I would like to thank you for your engagement in the course, and I wish you good luck for using CFD and also for the exam.